So the photoelectric effect is a result, one of the results of quantum mechanics. Okay, and as it turns out, this was Einstein's 1921 Nobel Prize. So this is some pretty cool stuff. So the way this works is when you shine light, and in this case, this is specific to a metal in vacuum. So you have to imagine, let's say this whole thing is inside a vacuum chamber. And the reason for that is so that you don't get interferences with the surrounding gases. Okay, gases can actually absorb some of the light that would be used in this experiment, or even can be ionized by these electrons. So this is all in a vacuum. Okay, and as it turns out, if you shine energetic enough light on a metal in vacuum, it will photoionize. Photoionize. So in other words, it'll eject an electron as a result of energetic light coming in and knocking that electron out. Okay? And so this picture shows you two cases. One in which a red photon at 700 nanometers is used, and one in which a UV photon at 200 nanometers is used. And if our metal were potassium, we would not observe anything happening when red light is being shined on this metal. We would not observe any photoionization or photoelectrons. But if we used a 200 nanometer photon, this would be energetic enough to knock out that electron. Okay? And so from this idea, Einstein came up with this equation. The kinetic energy of the electron that is ejected, so kinetic energy, because if you think about it now, this electron is in motion, so it's the energy that it has when it gets ejected is kinetic. The energy that it has when it's sitting in that metal is its potential, okay? And so this all equals h times nu, and we remember that h times nu is energy, and this is specifically energy of the photon, and I'll write another note that says that's the incident photon. So here is my incident photon. So that means the photon that's being used to drive this reaction, which is expressed right here, right? Potassium metal plus h nu. So we often use h nu to abbreviate photon or light. So we can use that in a chemical reaction by saying K plus light makes K plus plus an electron. It ejects an electron, okay? So now the kinetic energy of this ejected electron will equal the energy of the incident photon h nu minus what we call the work function. And that's just a fancy way of saying the energy required to remove the electron, okay? And so we could say phi equals also h times nu sub 0. We could also say phi equals hc over lambda. We could also say phi equals this energy that I have right here. So phi, this work function or energy required to move the electron, can also be related to this number. So for potassium, 1 mole of potassium requires 419 kilojoules of energy to remove 1 mole of electrons. So here's what we have to remember, and this is where this is going to be the hardest for our calculations. All of these h nu or hc over lambda calculations are for one single electron, not for 1 mole of electrons. However, this energy, this work function energy, if it's given to us as 419 kilojoule per mole, we have to convert it into joule per single atom. So we have to do that conversion to make this calculation possible, okay? So let's do that. Let's do this calculation.